We often talk about the frequency response of resonant RLC networks, but what about the transient or time domain response? I'm Professor Fiore, and I'll explain it to you right now. A lot of effort is spent on the frequency response of resonant circuits, but usually not a lot is said about the transient response, and that's a bit of a shame because it's very important and it's also pretty interesting. Here's really the bottom line, and that is resonant circuits, and in this case I'm thinking specifically of something like a parallel resonant RLC circuit, that will ring in the time domain. Now, what does ringing mean? What does it refer to? Basically, it means there's a damped sinusoid. In other words, a sine wave that is decreasing in amplitude and eventually disappears. That appears in various parts of your output signal. The frequency at which it rings is the resonant frequency of your system. Now, if you just have a sine wave driving your circuit, you're not really going to see a problem with ringing. It really occurs, you really see it when you have signals that have very quick changes in amplitude, very abrupt changes. So think of a pulse, a square wave, even something like a triangle wave. You know, you think of the peaks, the positive and negative peaks. There's a very quick, sudden change in direction. Not as fast as a square wave, but there is still this, sort of almost discontinuous, wave at that instant. You get that little pointy bit. Whenever you have something like that, you're going to see some ringing. Now, how much ringing will you see? That depends on the Q of your circuit. If you have a very high Q circuit, the ringing will last a long time. In other words, many cycles of whatever the ringing frequency is, whatever your resonant frequency is. So it's going to take that much longer for this thing to die away. In other words, to drop down ideally to zero, or at least below the noise level. Now, another way of looking at this is that Q is sometimes referred to in terms of its reciprocal, which is damping factor. So you'll hear about a circuit that has high damping or low damping. Depends a lot on what the application is. But basically, damping factor is just the reciprocal of Q. So if a circuit has a low Q, a small Q value, that means it has high damping. And if it has high damping, that means the ringing is sort of abrupt in a way. In other words, it disappears very quickly. It's heavily damped. So think of, like hitting a bell and it rings. Now, take some, large piece of felt or cloth or a towel or something and press that against the bell. That's damping, and right, the sound just sort of dies away very, very quickly. Another way of looking at this is to think in terms of, let's say, a weight, a mass that is suspended from a spring, and you touch it, right? You deflect it, and it bounces up and down. Because what's happening is the energy is going back and forth between being stored in the spring and then being stored in scare quotes here, in terms of the motion of the mass. In other words, the mass has momentum. So if you deflect it downward, then you release it, it flies back up, but it's not going to stop at the sort of stable point. It's going to go through that because we have momentum in that mass. Now, when it hits its highest point in that trajectory, well, the spring is, partially reduced tension compared to what it was. Let's put it that way. What ends up happening? Well, the mass has to start dropping again. And the process will continue because as that drops, guess what? It's not going to stop at the stable point again because the weight has momentum at this point that goes through there. And now what's happening is you're storing energy in the spring again, just like when you initially pushed it down. So this just goes back and forth, right? You see the mass just bopping up and down. Eventually, it dies away because of friction in the system. Now you can add more friction. In other words, you can add more damping by attaching something like a shock absorber, some kind of mechanical friction, to that mass, and that will make the damping disappear much quicker. All right, so without further ado, let's go look at a circuit. So I have a little RLC network over here. I'm going to drive it with a current source. So I've already done some calculations. Now, for a high Q parallel circuit, and by high Q we usually mean a Q of 10 or more, we can approximate the resonant frequency as 1 over 2 pi times the square root of LC. If you have a somewhat more modest Q, that's not spot on. And I explain this in the free AC circuit analysis text that I've written. And you can download that on my site, other locations, PDF or ODT, it's free. I explain this in some detail, but even a Q of like 3, 4, 5, 6, you'll still be pretty close, right? You'll be very close using this formula. But in any case, to be, really persnickety about it, I put an approximately equal to sign here. So you stuff in your 1 microfarad and your 10 millihenries, and you get approximately 1.59 kilohertz. Call it 1.6 kilohertz. Now, I would like to find out what my reactive values are at resonance. So X sub L and X sub C are going to be the same value, right? Roughly speaking, in a parallel circuit. So I grind this through 2 pi times the resonant frequency of 1.59 K times 10 millihenry, and you're going to wind up with 100 ohms. Now, the Q of the coil will be this X sub L divided by the resistance of the coil. So I've got a 20 ohm resistor I put in here. So we got 100 over 20, Q of 5. So not really high. I expect this frequency to be off a little bit, not like by a factor of 2, but a few percentage points probably. But this will be good enough for what we're doing. Now, I don't have any other resistors out here. I don't have any like parallel loads. Consequently, Q of the system is whatever Q of coil is. Remember, the Q of the system can't be any higher than Q coil. That's what sets the ceiling, so to speak. All right, so what I want to do is look at the time domain response, the transient response. Now, remember, if we were just doing a frequency domain response, we would consider what the impedance magnitude of this thing looks like. So at really, really low frequencies, the capacitor opens up, the inductor shorts, and all we're left with is our coil. So we would have some value, in this case 20 ohms, way down here in low frequencies. And then as we increase the frequency, right, C starts dropping, the X sub C starts dropping, but X sub L starts to increase. So we see that curve, that impedance magnitude start to rise. At some point, we are going to see X sub L and X sub C being approximately the same value. They basically cancel out. So we hit a peak, and then it starts to drop off, because even though X sub L continues to increase, X sub C now is on the other side. In other words, it's dropping. So the end result is the impedance continues to fall. Ideally, it will go towards 0, right? So we start off, in this case, at like 20 ohms. We come up to this impedance peak at about 1.6 kilohertz, and then it just continues to fall off towards 0. That's what we expect to see. And that impedance peak, right, is going to be Q times what your XL is, or Q squared times your R coil. But in this case, that's going to work out to be like 500 ohms. So in any case, what I've done here is I've thrown in a simple pulse. This is not something we typically use on our simulator, but it is very useful. And all this is just this little one-shot little pulse. I don't know what else to call it. In this case, I've set it to go up to an amp, and the width of this pulse is only 100 microseconds. And I've set it relatively small, and by relatively small, I mean small relative to the period that we calculated over here. If it's too small, you're not going to get enough amplitude out of here. But if it's too big, we're going to have some interactions that I don't want to see. So this just has to be, a bit faster than our calculated critical frequency. So let's see what happens. Now, so this pulse is just going to go from 0 up to an amp. It's only going to last for 100 microseconds. Then it's going to go back down to 0, and it's going to stay there. That's it. So let's see what happens. I'm going to come up here and do a transient analysis. And I'm going to run this from 0 to 50 milliseconds, which will be several cycles of this, right? I mean, 1 kilohertz is a millisecond. So I got 50 milliseconds here. We should see many, many cycles of a 1.6 kilohertz sine wave, assuming that's what we're going to get out of here. All righty. Open this up. All right. So hidden back here is a little tiny pulse. You probably can't see that. We'll separate the curves so that you can. So here's my pulse, right, in green, just going up to an amp, dropping, and that's the end of it. And then we have over here the V out, right? So we see the energy sort of bouncing back and forth between the capacitor and the inductor. And while that's happening, we're getting some dissipation in the coil. The energy is getting sapped away, you know, like a frictional element in a mechanical system. And eventually this thing stops, right? You know, another thing you can think of is like a pendulum or a kid on a swing. You give him one good push, right? One good push, and he swings out and back and forth, and you know, and eventually Sally is perfectly still, right? Okay. So, all right, that seems good enough. Let's collect those up again. All right, so we can see that pretty well. Now I'm going to turn around and I'm going to increase the Q by dropping the coil resistance. All right. So, you know, we could drop it down to, I don't know, let's say this is a Q of 5. So if we dropped it down to maybe 2 ohms, right, drop it by a factor of 10, now we're going to get a Q of 50. That's a very high Q circuit. Very little damping is the other way of looking at it. So when I redo this, I would expect this to ring a long time. And sure enough, here we go, right? So here's the preceding one, right? This is pretty much gone somewhere around, I don't know, 5, 6 milliseconds, right? There's 5 right there. So you get to 6 milliseconds. And this is, you know, way, way, way down, orders of magnitude down. But in this case, with a much smaller R coil giving us a much higher Q, this thing is ringing like crazy. Now I'm going to zoom in on here. Let's see, I don't want to see too many cycles, just a few. And what I'm going to do is I'm going to kind of figure out by dropping a couple of these little cursors, we'll see what the frequency of this ringing is. Like I said, this should be around our resonant frequency. So 1 over 1.6 kilohertz is like 620, 30, something like that, microseconds. So the difference we're getting over here in the X domain, right, A minus B, is 646 microseconds. So that's right where we expect to be, right? This is going to just ring out like this. Now, get rid of that. Okay. That's what we get from our little pulse. So what ends up happening if, like I said, we put in a waveform that's not a sinusoid? I'm going to bring this back to our original 20 ohms, right? Back to our Q of 5. So let's say that we take our source and instead of having a pulse, let's put a square wave in. All right. I'm going to leave it at 1 amp and I'm going to use a default of 50 hertz. Now, before I do anything, that leading edge on the square wave looks an awful lot like that impulse that we put in just a moment ago. So what do you think is going to happen? Well, this is where the term ringing comes from. Wow. So you can see the square wave sort of embedded in here. It's popping up and down. While the green is really it. We could separate these so you can see it, right? So there's our input. Notice on each of the edges, whether it's the positive or the negative going edge, what ends up happening? We get this ring. In other words, this is perfectly reminiscent of what we had back here. Okay, let's combine the curves so you can see this a little better, right? I'm just going to go back and forth. All right, so there's just the 1. And there it is with the square wave. So you can see basically what it's doing is it's taking this thing, right? And it's just doing it on every single edge, whether it's a positive going edge or a negative going edge. So this is crazy ringing, right? You look at a square wave and you see this, you know it's going through a highly resonant circuit. There's not much damping there. So, when we do like filter work and stuff like that, we're always concerned about the Q or the damping factor. If we don't control it enough, our square waves turn into these crazy looking things. All right. So what about, I don't know. How about a triangle wave? That's kind of abrupt. It's not like a square wave, but there is this rather abrupt change right on the peaks. Let's see what that does. Again, I'm going to use the default 1 amp, 50 hertz. Let's see what this thing does. Okay, so this is coming up. We see these weird little, I don't know what you want to call them. You can imagine sort of the straight edge here going back, and this is that initial sort of ring transient coming in here. All right, and it's just distorting the waveform. Now let's go back to our square wave. All right, so remember the square wave gave us this with this particular version of the circuit. So I want to come in and change my arc coil again. What do you think is going to happen if we drop this down, right? Let's drop this down to 10 ohms instead of 20. So that's going to double up the value of the Q, right? So we had a Q that was sitting at 5, now the Q is at 10. And as I said, the amount of ring, the time for this before it goes to 0, is a function of the Q. So what would we expect? We would expect this thing to ring out a bit longer. And exactly that's what we see, right? Oops, go there, right? So you can see we're getting a few cycles here, and we increase the Q, we reduce the damping, and we get more, right? You can still see the square wave kind of hiding in there, but this is what we see. And if we went the other way, if we increase the damping, so let's just grab that, right? So let's say, we had 20, if we went to like maybe 50 or something like that, now it's a very low Q. It's only a Q of like 2, okay? All right, so now we just see just a couple little wink kind of things, right? The square wave is sort of more easy. It's easier to see. We're getting a lot of overshoot here, and then just a couple of cycles and off we go. Okay, beautiful. So that's the basic drill. If you run high Q, and one of the reasons we run high Q is because we want these highly selective sort of circuits. But you have to remember, you're not always dealing with sine waves. If you're throwing in signals, around the resonant frequency, it's a sinusoid, you get this sort of Q amplification effect, which is really great. But if you try to put in something else, like a digital pulse train, you can really destroy the look of that pulse train in the time domain. All right, so it's just another way of looking at the response of the network. Okay, well, I hope you've enjoyed this. I hope you've learned something from it. And until next time, this is Professor Fiore saying, take care.